All right, here we go. Let's get rolling. We're going to talk trapezoidal approximations, but before we do, we need to talk about this thing, Riemann sum. So we kind of addressed it last section. I wasn't ready to talk about it then. It was too soon. Now we're ready to talk about what a Riemann sum is, and there's a picture of Riemann himself. He's a famous German mathematician. Don't be confused with a Wee-Man sum. The famous reality TV guy from MTV. Actually, I'm just kidding. He doesn't have his own math saying. True story, I walked right past Wee Man once in the store. I was like, hey, that's Wee Man. And I guess he was there signing monsters or something. So that's my little claim to fame. So let's take a look. Forget about the reality. Oops, he doesn't want to leave. Can I get rid of him? All right, so what is a Riemann sum? So we were doing these approximations last time with these rectangles. It doesn't matter which one, left hand, right hand, midpoint. Let's just real quick draw one. So if I wanted to approximate the area under the curve, so the whole thing is this area under the curve. Let's just do a couple left hand right here. So, ooh, a little rough right there. So this is very, very rough. So we've got this idea going on here. I've got a left hand approximation, so it's going to be a little short on this. And what am I going to do? The idea is I can get a better approximation. I'm trying to get the whole area the more rectangles I do. So I made this cool little video last time about how many rectangles under the curve. So check out this picture. I've got that x squared plus 1 with the 4 rectangles with the left endpoint. And check it out as I add a rectangle. 5, 6, 7, 8, 9, 10. So I didn't want to draw all this out. That'd be crazy. But check this out. What's happening? What am I doing here? 15, 16, 17, 18, 19, 20. Oh my goodness, I'm up to 30, 40, 50, yeah, I'm all the way out to 100. They're so small you can't even see them. What does that represent? Look at that. That's the area under the curve. And I'm only at 100 rectangles. Imagine if I was at 1,000,000 or 1,000,000,000 or maybe even the limit as x approaches to infinity. I don't know. So I want an infinite amount of rectangles. That'll get me the complete area under the curve because those rectangles will be so small. Each little slice is going to give me the area under the curve. Excellent. So I'm trying to get an infinite amount of rectangles. So let's do that. So what we're going to do is we're going to take just the area of these rectangles, just the basic length times width or base times height, however you want to think about it, and we're going to make this crazy formula. So you can wait, I guess, till the end if you want to just follow along with how I get this formula. But basically all we're going to do is the base of this times the height of this. So, and I'm going to change the order actually just so it's a little bit easier for us, is I want the base to be the second one. So I'm going to go height times base. So what am I going to do here? Well, if I'm dividing this into infinite rectangles, it needs to be generic. So I can't just do it for 4. I just put numbers in. I'm going to do it, pretend that I'm trying to do every single rectangle possible going towards infinity. So that's my ultimate goal here. So what am I going to do? Well, I'm going to say, well, the width of this, I'm going to call this my change in x. So maybe you've seen this in a slope formula, your change in y over your change in x. So something like that. This is my change in x. This is the width right here. So I'm going to that'll give me the length, and it's changing. As I get to smaller rectangles, that's going to be a smaller number. So we're trying to get that to be really thin slices. What's the height of this thing? Well, it's just the f of x, isn't it? So it's the f of x. But what am I plugging in there? Let's call it c. So each time I put one of these endpoints in, I'm going to say it's a constant. I'm putting in these constants. Now, yeah, I can count these up, the different constants I have, but really we're going to number them. This would be my first one, my second one, my third one, my fourth one. And what am I going to do here? I'm going to put c in there, but it's going to change. So I'm going to call it c subset I. So as this counts up to infinity, this will give me all of my heights right there. So there's the area. So how do I count that to infinity? Well, I need a summation. So maybe you remember this from series and sequences. I can sum up all of my numbers. What am I going to do? I'm going to start when I is 1. And what am I going to do? I'm actually going to go to n, the letter n, because now in this case, what would it be? I would have 4 rectangles, it would be 4. So I could put in 4. And go 1, 2, 3, 4. But I want to go to n. Why do I want to go to n? I want to go to infinity. So what am I going to do out here? I'm going to take the limit as n approaches infinity. Boom. That is it right there. That is pretty awesome. Let me get these guys out of the way here a little bit so we have room to work. So that is the formula that Riemann came up with here for infinite rectangles. And it's just base times height is all it is. But this is pretty cool. So what does this actually equal? Well, this is like the longhand form of like a derivative. This is going to equal something new called the integral. So this is the symbol. It's like a weird looking S, kind of elongated here. And we're going to say of a function and then with respect to x, this dx right here. So this is the notation that we're going to come up with for finding the true area under the curve. So if we want to find the area under the curve, we're going to take the integral of the f of x dx right there. Pretty awesome. So if you want to have it written out pretty, I actually wrote it out pretty here for you. There it is. That's better than my handwriting. So we're doing integrals. We're going to actually do one longhand is pretty intense. You have to have a really good understanding of the series and sequences. We're not going to go that in depth. We're going to show you the algebraic way to do it. And in fact, this video, I'm just going to have the calculator do it because the calculator is really good at it, and it does it very quickly. Think of it like this. It's pretty much, remember how we did this in chapter 1 or 2 or something? You know, there's a longhand definition of derivative. That's the notation for it. This is the longhand thing of an integral. That's an integral. So that is our ultimate goal right there. For finding the total area under the curve. So when we do it, it's going to give me actually everything. Forget the rectangles. They're so thin. There's like little slices. It gives me all the total area. Pretty awesome. So let's take it and label a couple parts on this. All right, so here we go. This is a much better picture. This is called the definite integral. We are going to define an integral. So you can see I cleaned it up really instead of my little shading. If I want to find the area under the curve from the interval from 1 to 3, so let's first write this as an integral. What would this look like? Well, this would look like the integral from 1 to 3, and you can write as the function, or we can actually put the function in there, of x squared plus 1 dx. So that is what it's going to look like. This is going to represent the area under the curve, and we're going to find that in the calculator. And in the next chapter, I'm going to show you how to do it algebraically. So let's label some parts of this just so we know what they are. So from a to b is the interval, so we call this the lower limit. So this is the lower limit, is the a. So we're always going to start with this, the lower limit goes to the upper limit. Ooh, my handwriting is a little rough today. And that's the b. So that's where I had this interval. I think on the last one I wrote from 1 to 3. So we integrated from 1 to 3. The part, the f of x, is called the integrand because it's awesome. It's grand. That's the thing we're integrating. And then over here is going to be your variable of integration. So this just tells you what variable we are integrating. Integration. And this can be anything. This could be, you know, you could do a velocity or something. dt. It just tells you what variable you're in here, and then you could define it from whatever a to b or whatever the interval is there. So that is all the parts. This is how we write it. Can we evaluate it? Sure, man. Let's go to the calculator and do it. Let me clear out here. So if I want to evaluate this, there's 2 different ways. This time I'm going to show you how to do it with Math 9. So if you go to Math, you can scroll down to number 9 or just hit number 9. I kind of want to show you what it is. I think it's fn int is what it's going to say. So remember, we could find n derivative. We could find the derivative. This is the function integral. We can find the fn int. You just hit enter. So if you have the new operating system, it's awesome. I mean, it's ready to go. You just type in this case, we're looking from the lower limit is 1, upper limit is 3. What is my function? Just type that bad boy in there. So it looks really nice with the new operating system and with respect to x. So type it in just as it looks. I mean, there it is. And then what happens? Hit enter. Oh my goodness, that is the answer. So we could have sat there and drawn 100 rectangles, and we would get closer and closer and closer to this number. This is the number. This is the actual answer. This is the area under the curve. This is pretty awesome. If you don't have the new operating system, you can still do your Math 9, but it looks something like this. Sorry, I couldn't get the old operating system up. It's too old school. But basically, this is your integrand. This is your function. This is with respect to, this is your dx. So this is with like what your variable of integration. And then there's your lower limit and there's your upper limit. So that's the notation. If you're old school, it still works out great. It just doesn't look, it's not as user friendly on that. Awesome. So let's use this idea now. So we're going to use it to kind of get the right answer, but we're still going to do some approximation because I saved this one. It didn't matter before if we use left, right, middle when you're talking about this definite integral because we're doing infinitely many. They're so small. But when we are doing just a couple, this is a really, really good approximation. Why is trapezoid so good? Well, check it out. If I want 2 trapezoids in here, so let's say I'm going to do 2 trapezoids, same interval, 1 to 3. I know the answer. I know it's 10.666. Repeating. But check it out. Instead of doing like little rectangles here, what if we made these trapezoid. So if I just connect the dots here and here, so remember trapezoids, these are like right angled trapezoids because look at that. These are the right angles. I just rotated it, or I guess you could think of it like this. I'm doing trapezoids like this. Look how good they are, and if you had better, if you could draw a little straighter, that's pretty awesome, isn't it? What if I broke it into 4? So I still do my intervals, break it into 4 here, and we're just going to do that. So I'm still breaking it in, but instead of rectangles, I'm connecting the dots. And look at that. Do you see how there's barely any area above the curve? I'm slightly above the curve in this case. And then if we get even closer to 6, so we're looking at 3, we got 3 in there, and then we're going to draw that. Ooh, get in there. Okay, there we go. And let's draw them in there. And then look at this one. If I connect all these dots, boom. So check it out. So even with 2 is actually not too bad. Look at 4 is pretty good, and look at 6 already. It's really great. So this is actually even closer than some of those rectangles we were using. So let's just do one for n equals 4 because you're going to have to do this by hand. So if I'm going to break this into 4 rectangles, it's still the same thing. You know, you still got to find your b minus a divided by n. So 3 minus 1 over 4. So we're looking at each interval is a half wide. And you can tell here that's 1, that's 1.5, that's 2, that's 2.5. Now I don't want to do all these, but let's just do the middle one to kind of get an idea of n is 4. So we still do the same thing. But I need to know what is the area of a trapezoid. Do you remember geometry? You add your bases, b1, b2, times it by your height, and then you divide it all by 2. Do you remember doing that? So why do we do that? Why do we do our base 1, base 2? If we look back at our formula, it's nice. Our height's a right angle, so we don't have to do any work. We have the height right there. It's on its side. So why are we doing that? Well, basically, it's a rectangle. It's just base times height, but we're averaging our bases. So if this one only goes to here, if this one goes to here, we're actually thinking about a rectangle when you average it. B1 plus B2 divided by 2 would give you the rectangle right in the middle there. And basically, you're finding the area of this. So that little chunk there makes up for that chunk over there. So you average your bases, and then what? Once you average your bases, you times it by your height. So in books, or if you Google it or whatever, it's going to give you a long formal definition, which is good. It's a good definition if you're going to do 20, 30 rectangles. But we're going to do 4, maybe 6. Crazy. Maybe we'll do 8. I don't know. I like to actually just write them out. I think it's easier to see what's going on. There is a little bit of a shortcut, but I think it's, for us and our purposes, we're going to write each one out. And maybe we can take the height out at the end. So let's do this. So what do I have to do here? If I was going to do this problem here, I'm going to say what? I'm going to say base 1 plus base 2. So I'm going to say, we'll write this one out, the f of 1 plus the f of 1.5. And I'm going to divide that bad boy by 2. And then I'm going to times it by the height. So it's this times that by the height. Then what am I going to do? I'm going to do the next one, the f of what? 1.5 right here. Then I'm going to add it to this. So I'm on the next rectangle plus the f of 2. Going to divide that by 2, times it by the height. So that'll give me, so this one gives me that trapezoid. This one gives me that trapezoid. Let's keep this train rolling here. I've got the f of what? The f of 2 plus the f of 2.5. Average that out, times it by the height. And then the last one, I hope I have enough room here. I'm going to do that last rectangle. Let me slide some of this over here. Woo! Got some room, but my arrows are not working now. All right, so add the last trapezoid in here. So I'm going from 2.5 to 3. So I'm going to say the f of 2.5 plus the f of 3. Divide that by 2, times it by h. So when we have it this far, if you're good with that, I'm going to slide down a little bit, get us a little room. We are trying to find out how close we are to the true value, which is what we're getting to here in a second. What can I do? Well, you notice they all have h in common. So if you want to, in this case, you can take the h out and times it by all those averages. And again, we're going to go calculator on this bad boy. And I think I need to put my function in there. So if my function is x squared plus 1, a lot of these we can do in our head, but with those decimals, make sure you are in independent variable is under ask. So it's just like the last time. Remember we were going to our table and saying, okay, here I got to find all the different intervals, and I'm counting by a half, and we went up to 3, so this one. Excellent. So there are my numbers. I'm going to cheat and kind of throw them in here so I have something to look at. So we can just go ahead and throw these in. The f of 1 plus the f of 1.5 is going to be what? If we just combine it, can we combine them? Is that okay? 5.25 divided by 2 plus, what are we going to do? The next one, we're going to say 1.5 to 2 is going to be 8.25 divided by 2. So I'm just adding them. 3.25 plus 5, 8.25 divided by 2. Blah, blah, blah. Put the next one in, the f of 2. So we'll add these together, 12.25. Divide that by 2. And then the last one is what? 7.25 and 10, 17.25 all over 2. What is h? You know, I wrote h here because we factored it out, but let's go ahead and put h. What is the width of each interval? It is 1/2. So if I want to evaluate this and see how close I am to the 10.6 repeating, let's type all these in. So I'm going to say it's 1/2 times, we've got 5.25 divided by 2 plus 8.25. This is so exciting. How close are we going to get? Plus 12.25 divided by 2 plus 17.25 divided by 2. So there it is. I know you're really excited to see how close we are. I know, it's like suspenseful here. What do you think? Over or under? Let's do the over-under on this one. Am I over or under? If you, maybe you can tell from my pictures, but basically this is a concave up picture. So when you do concave up, what do you think is going to happen? You're actually going to be slightly over. So it's a set rule for trapezoid. If it's concave up, you're going to be slightly above. And what do we get? 10.75. So pretty close, huh? With just 4 trapezoids, 4 approximations, 4 subintervals, I got 10.75. I'm pretty close, so that's pretty awesome. So if it's concave up, it's going to be a bit of an overestimate. If it's concave down, it's going to be an underestimate. You're going to be below it. Underestimate. Don't be confused with under armor. Underestimate. All right, let's get going on these and talk about use the notation. So here it is. So I gave a new function here. Can we use the trapezoid rule? So if you want to draw yourself a little sketch, a little picture, you're more than welcome to. You definitely got to find your b minus a all over n. So I want 3 sub intervals of the trapezoid rule. So I'm looking at 3 over 3, which is 1. So I hooked you up here. Maybe you don't need a picture. I like pictures. I think they're kind of fun. So this is going to be really rough. I know this is 10 minus x squared, so I know it's a parabola upside down. That is an awful, I can't live with that. Let's try that again. That is not much better, but I'm going to keep it. I can live with that one. So what am I doing? I'm going from -1 to 2, and I'm finding the area under the curve. I'm finding all of this right here. So this is what I'm finding. There it is right there. And I'm breaking it into 3 intervals. So I've got the f of -1, the f of 0, the f of 1, and the f of 2. So you can see, hopefully you can see my different trapezoids in there that are green. I've got 3 trapezoids. And let's knock this bad boy out. So, again, we're gonna have to use a calculator here to get some of these values here, but I'm gonna find the trapezoid of each of these. So, do we run it out? Let's write it all out. I'm gonna kind of speed it up here when I write this all out.
So I'm gonna take the height times the f of -1, f of 0, all over 2, plus the f of 0 to the f of 1, all over 2, plus the f of 1, all over 2, and I'm done there. Excellent. So let's evaluate some of these numbers here. Change my function to 10 minus x squared. And go to my table. And let's go to new values. We're looking at -1 to 0 to 1 to 2. And let's delete that bad boy. So there are my numbers right there. I'm going to put them underneath. And now we can plug them in here. We're going to say the interval is 1. The f of -1 is going to be 9 plus 10 over 2 plus 10 plus 9 over 2 plus 9 plus 6 over 2. Awesome. This one works out pretty nice, doesn't it? So that's just going to give me, we can type it in. If I come back over here. And what are we going to get? We're going to get, screw this out, 19 over 2 will be the first one. And you can times it all by 1 if you want, but it's just going to times 1. We're going to add to it. That's nice, 19 divided by 2, that's pretty cool. Plus 15 divided by 2, hit enter.
26.5. 26.5. Is this an over or under estimate of it? Oh, it's part B. So is it an over and under? Well, since it's concave down, this should be underestimate. So it's going to be underestimate. Let's find the calculator and get the exact value here. So I can go to math number 9, and I'm going to evaluate the integral from what? From -1 to 2 of my function 10 minus x squared with respect to x. Boom. 27. So the calculator says 27. Whoa, where'd that go? Calculator says 27. We got 26.5. Pretty good approximation there. So we were a half off. Awesome. So that's how it's going to look using the definite integral there. Alright, so I'm going kind of quickly here because it's so similar to the last one. We're just using trapezoid instead of rectangle. So I'm going to do one more example here and cut you loose. We just got to do them. I know they're kind of tedious, but they're kind of fun in a weird way too. So same thing, what if they're not uniform intervals? So if you want to draw yourself a little sketch here, you can. The main thing to realize here is I'm not counting by an even interval here, so some trapezoids are going to be a little fatter than other ones here. So can I break this into 4 subintervals? So this is what we're finding here. I'm sorry, I didn't read the problem. So we're talking about, I always wanted to open a coffee shop called Starburst. That's my dream someday, Starburst. So there's my function. And so I've got a table of selected values of 10 hours. This is something new here. At t equals 0, I've already served 200 customers. So then, for some weird reason, I start my clock and say, okay, at time 0, I'm serving 37 people per hour. At the second hour, I do 44 people per hour. So I'm showing how many people per hour. So this is a rate. So what I'm going to do is I'm going to find the area under the curve here. Or I'm going to integrate the rate of people per hour. Kind of interesting here. So let's do it. So the first rectangle, remember, will be from here to here. So I'm looking at, if you want to draw a picture, you can, but I'm looking at, now here we can't just pull the h out because what is the h? The distance here is 2. They're 2 apart, times my base 1, 37, plus 44, all over 2. So I got to average out the heights. Plus, let's look at the next one, and maybe I can just slide that over, yeah? Oops, it's not a group. That would have been nicer if it would all slid over together. So now I'm going to look at this one. What am I doing here? I'm going to say the difference between 2 to 3 is 1. And then what are my bases here? I've got 44 plus 36 divided by 2. Then I'm going to slide it over again. Nope, I'm going to slide this over again and look at this one. And what am I got going on here? I'm going to say from 3 to 6 is 3. And what's going on here? I'm going to say 36 plus 42 all over 2 because we're averaging them. And then my last one I'm going to do it. I'm going to make these, oh dang it, I thought I could make them uniform. Let's just finish it out. There we go. Alright, so I've got the last one from 6 to 10. That width would be 4. And then what are my heights? 42 plus 48. Average them out. So that is it right there using the table. And then it's just a lot of crunching numbers here. So however you want to do it, you can type it all in. It's going to be 2 times. What I usually do is, okay, I lied on that. I usually do these averages first because it's an extra set of parentheses because you got to go 37 plus 44. You got to hit enter or put in parentheses. So I do actually kind of write these out first. So I've got 40.5 times 2. The next one times 1 is nice. I'm going 44 plus 36. Hit enter, divide by 2. Probably didn't need a calculator for that, Mr. Brust. That's okay. Then the next one, if you want to times it by the 1, you're more than welcome to. Then we're going to go, oops, I can't see it, 36 and 42, is that right? 36 plus 42, hit enter, divide it by 2, you get 39, so it's 3 times 39. And then the last one's going to be 4 times 9, I'm going to do it in my head, crazy. 90 divided by 2 is 45. Look at that mental math. Wow. Wow. Now I'm not going to go calculator. I'm going to type all of that in. So I'm going to say 2 times 40.5 plus 1 times 40 plus 3 times 39. And the calculator can handle order of operations in this case because it's just adding and multiplying. Not a problem, so you don't really need to worry about parentheses here. Plug these in, and what do I get? 418. That is awesome. So it's 418. Can we put this in context to what's going on here? So notice it says approximately, because I'm finding approximate. Approximately how many customers have I served after 10 hours? So this is the total customer served, because this is a rate of change. You can integrate it, and it gives you the total. This would have been the total people served. 418 people were served over that 10-hour time period. But I want to know how many had been served after 10 hours. Don't forget that I had already served 200. So really, after the 10-hour time period, I know during the 10 hours I served 418. I started with 200, so I actually served approximately 618 people. Starburst. Look for it. That is it. Good luck on the practice and the master check.
Peace out.